Good morning. There we go. That in. Okay. Sweet. So today I wanted to do a few things. I want to go back over those trig derivatives a little bit more slowly. The sine and cosine derivatives, I'm hoping we're feeling a little bit more comfy with. Had some time to digest those arguments, and if you look in the modules, I've added a whole bunch of stuff for you guys to play with. That hopefully will make these a little bit more tractable. But at the end of the day, when it comes to the 3.3 stuff, the derivatives of trig functions section, what's really important is that you remember those two special limits. The derivatives of sine and cosine are, of course, supremely important. And then the rest of the derivatives of the trig functions are a big deal as well. Remind you the basics. Today is, of course, this is, of course, Calc 1, and today is, shit, what is it, the 15th? Yeah. Today. The other thing we're going to do today is talk about the chain rule, which is the last differentiation technique that you're going to learn. So, people say Calc 1 is all about derivatives. That's really not true. We have pretty much learned all the derivatives we're going to learn, with the exception of the chain rule and a few other kind of tricky things that require the chain rule, like implicit differentiation and logarithmic differentiation. Really, once we've done those things, we will be done with all the differentiation techniques, and we'll be moving on to applications of the derivative. So we'll start looking at things like related rates problems, stuff that essentially are like baby differential equations. And we'll also look at how we can use derivative information to get really, really good graphs of functions, stuff like that, things that you can do with the derivative. But we're almost done learning how to differentiate. Before we move into that, though, I just want to go quickly over these again. Important limits from section 3.2. You can write it in terms of h or theta, like we did as we were working the differentiation problem itself. Or you can just write it in terms of x. That's the variable most people are used to using. So lim x to 0 sine x over x equals 1. And lim x to 0 cos x minus 1 over x. This is 0. So these were two important limits that came up while we were discovering the derivatives of the trig functions. We proved this guy geometrically, and then we proved this guy as a consequence of this guy. You don't have to remember the geometric proofs. That's not necessary, but you do need to remember the results. And there are some problems in your homework that are going to ask you to play around with these and cook up some other limits using just these as your kind of baseline. And I'll show you one or two little things like that here today. But first I want to recap the other main results and kind of go back through the other trig derivatives. I interrupted Daddy's class, you know that? Yes, you are. But you're doing it with such cute style, it's okay. All right. So using these, we were able to calculate the derivatives of sine and cosine. And those are the, the main results from section 3.2. 3.2 is a whole lot of work to get what looks like not a whole lot of result. But in fact, these are major results. And one of the things I posted to the modules on Canvas, if you haven't had the chance to take a look at it, are a bunch of graphs involving functions and their derivatives. So here's an example, 1 plus sine x, of a function that we could not have differentiated before. Here, I've got a bigger over here. So before we finished section 3.2, we could not have come up with the derivative of this function. We could have differentiated the x piece, but we could not have differentiated the sine x piece. But now that we do have those derivatives, we can. So x differentiates to 1, and sine x differentiates to cos x. So g of x here is f primed. It's the derivative. And what you'll notice is that everywhere the blue graph is above the x-axis, and everywhere the red graph is increasing. In fact, the only times where the red graph kind of stops increasing just for a second is right here, where the blue graph touches the x-axis. And that's where we have these horizontal tangent lines. So I think if you haven't yet, play around with this a little bit. I think you'll have some fun. I think it does a good job of illustrating what derivatives do. I posted a couple more things like this to your modules to kind of help you get a better visual feel. But the upshot is, we got some derivative stuff that we couldn't have gotten before. Okay. As a consequence of this, so using the quotient rule, we found that the derivative of tangent, which we calculated as the derivative of sine x over cos x, right? We're using the quotient rule, so low d high minus high d low over low low came out to be, I'll do this one on in full, so this is your low d high, bottom times the derivative of the top, minus high d low, top times the derivative of the bottom, all over low low, the bottom squared. This is cos x times cos x, which is cos squared x, minus sine x times negative sine x, all over cos squared x. If you finish cleaning up the top, you can't cancel these. If you finish cleaning up the top, you get cos squared x plus sine squared x over cos squared x. And of course, cos squared x plus sine squared x, that's 1. So this is 1 over cos squared x, which has another name, that's secant squared x, because the reciprocal of cosine is secant. So the derivative of tangent is secant squared. And we got the other ones as well. I don't want to spend too much time today going through the quotient rule arguments because they're not fun or exciting. But in total, so all in all, if you missed the quotient rule argument that led us to the derivatives of the trig functions last time, you should go through them. I think I did tangent and secant for you, and then said you should do cotangent and cosecant on your own. There are some problems in your homework that ask you to cook up derivatives like that, so it's good practice. Tangent differentiated to secant squared. I'll write the cofunction derivatives over here. Cotangent differentiates to negative cosecant squared. Secant x, the derivative ddx of secant x was secant tangent. And cosecant is negative cosecant x cotangent x. So you see a pattern here, right? Between the regular trig function and its cofunction. The same pattern in the derivatives that you see between sine and cosine holds down here for the secant and tangent functions. The derivative of tangent is secant squared. The derivative of cotangent is his cosecant function squared, but with a negative. So tangent secant squared, cotangent negative cosecant squared. Secant differentiates to secant tangent. Cosecant differentiates to negative cosecant cotangent. So for these guys, if you remember these two, the tangent and secant derivatives, you can get the cotangent and cosecant derivatives just by remembering to swap the functions for their cofunctions, secant squared to cosecant squared, and popping out a negative. There is a reason for this. It's because the cofunctions, remember where they come from, are the same functions, if you think about things in terms of the triangle, just 90 degrees out of phase, coming from the other angle, the complementary angle in that triangle definition. So there's lots of ways to interpret this. But for us right now, what's important is that you remember it. So please remember the derivatives of the trig functions. All right, all together. If you want them in one place, here they are. All right, so this was kind of the payday in section 3.2. We now know the derivatives of all 6 trig functions. What do we do with this? You do stuff like that Desmos graph, right? You're going to find horizontal tangents for trig functions. You're going to find places where trig functions are increasing or decreasing. You're going to sketch the graphs of the derivatives of trig functions, which means you need to know the graphs of the trig functions really well. So if your trigonometry class was a little bit light on graphing, especially when it comes to the sine and cosine waves, you really do want to review that stuff. Make sure you know your graphs, sine, cosine, secant, and tangent at least. There's a question in chat there. Do we need to know our trig identities for the test? Yes. I could well ask you to do something like this. I've hinted at it several times now, right? That you should come up with the derivatives of cosecant or cotangent on your own. And this last step here, I would not have been able to do that unless I knew my trig identities. Here to here is a trig identity, saying sine squared plus cos squared is 1. Here to here is a trig identity, saying 1 over cosine x is secant x. And if I didn't know both of those, I couldn't have made that argument. And I may well ask you to do something like that on the test. So yes, you definitely need to know your trig identities. If those feel a little bit weak, again, look at the resources page on Canvas. So if you go on, not resources, I'm sorry, modules page in Canvas, the very top module there is a review, like resources, and there's a meaningful chunk of that dedicated to trigonometry. So if you're feeling a little bit lost when it comes to trig identities, if you haven't needed them in a while, please go take a look at that stuff. Make sure that you're feeling at least a little bit comfy. I'll do an example or two involving these things, but it's going to come down to the time you put into the homework, and making sure that you remember the stuff from trig that you should remember. That's very nice, Angelica. Okay, so I want to look at some of the limits I mentioned. These two special limits here have some fun consequences. They allow us to calculate other hard limits quickly in terms of them. So let's look at one or two problems like that. There are a few in your homework, and they do make good test problems. So I want to make sure that we've seen plenty of examples. And then we're going to talk about the chain rule. All right. So this is a classic Calc 1 problem that stumps many people. I don't want it to stump you. It looks a lot like the limit that we talked about at the very start of class, the sine x over x limit. It's the limit as theta goes to 0 of the sine of 2 theta divided by 3 theta. Remember what multiplying by 2 on the inside of the sine function does? It changes the period, right? So this sine function is oscillating twice as fast as the regular sine function. But then instead of dividing out just by x or just by theta, I'm dividing out by 3 theta. So the sine function upstairs is oscillating faster. The bottom downstairs is getting bigger faster, or getting smaller faster, I'm sorry, as theta goes to 0, because the slope of the bottom is steeper. And we wondered, does that have some effect on the limit? The answer is yes, it does. This limit is not 1, even though it still looks like 0 over 0, right? If I plug 0 in, the top is 0 because the sine of 0 is 0. And of course, the bottom is 0 because 3 times 0 is 0. So plugging in, definitely not going to do the job. What will work here is a little substitution. So remember back when we were working a lot with limits, there were some that we liked to say, oh, well, if this algebra is a little bit confusing, or if compartmentalizing is a little bit confusing, you might want to make a substitution. This is a perfect example of a limit problem where you'd want to do that. Before I do that, though, this 3 downstairs, he actually can come out. So I'll do this in a couple steps to make sure everybody can see where it's going. Okay, do you agree that having a 3 downstairs is the same as having a factor of 1/3 out front? I hope you do, because it's true. You know, we multiply fractions straight across, so if you were to multiply that fraction with the other fraction, you would get the thing we started with. And the good news is this 1/3, totally constant, right? No thetas in him. So he can come out front the limit. And now this is looking a little bit more like our sine x over x limit. There's one more thing I want to do to try and make this look as much like that sine x over x limit as possible. And that's to make the variable stuff in the denominator match the variable stuff in the numerator. So rather than having sine 2 theta over theta, I would like to get to a place where I have sine 2 theta over 2 theta. And the easy way to do that is to multiply by 2 over 2. Now the 2 that's upstairs, I'm going to bring out front to hang out with my 1/3. But the 2 that's downstairs, I'm going to group that with the theta in the bottom. So the 2 that's upstairs will come out front to make that 1/3 of 2/3. And then what's left is lim theta to 0, sine 2 theta over 2 theta. So this fellow came out here. This fellow came in there, which is all algebraically totally kosher, because everything here is just being multiplied. And the result is this, which looks a lot like my sine x over x limit from the very start of class, right? It looks very much like this guy. At this stage, depending on how comfortable you are, you can either declare this limit to be 1 based on the sine x over x limit, or you can make a little substitution, and that might help you see it. If I let x be 2 theta, then as theta goes to 0, x goes to 0 too. X is just 2 theta, so yeah, good. So there's a little discussion in chat. Why all this fiddling with constants? My goal here is to make this look like sine x over x. In other words, my goal is to get this to be sine of something over that very same thing. So I want the thing that's in the denominator to be the same thing that's in the sine function in the numerator. So first I had to get rid of the 3, and then I had to introduce a 2. Right? I started out with sine 2 theta over 3 theta, and my goal is to get this piece downstairs here to be the same as this piece, the inside of the sine function upstairs. So I had to get rid of the 3 and then introduce a 2. And I just did that in separate steps. If I make the substitution now, x equals 2 theta, then this becomes the limit as x goes to 0, sine x over x. And that's the limit I know to be 1. So what do we get out of this? This is 1 by our special limit. So the whole limit is just 2/3. So this is a little bit sneaky, but it's a fun trick. And it's one of those things that we just have to do to everybody in Calc 1, because the value of this limit is easy to underestimate. The value of this trick is easy to underestimate. And they're useful tricks that you'll see not just here, but also in the end of this class when we go to make substitutions in integrals. You'll see it in differential equations. You'll see it in Calc 2. So it's worthwhile to understand what's going on. Good, good. I'm glad to. So my goal is to get whatever weird trig limit I'm given into the form sine x over x as x goes to 0, or cos x minus 1 over x as x goes to 0. And we can juggle and manipulate constants. We can do whatever algebra tricks we want in order to make stuff like that show up. Any questions on this fella? There is one more like this that I wanted to do really quickly. Just to make sure we're feeling comfy, and because it is sometimes treated as a special limit on its own, but we can get it out of the sine x over x limit. Albert asked a fair question. In the real world, what's this used for? Remember that sync function? I'll be very brief here. So in signal processing, this function has a special name. It's called the sync function. Get this out of the way. It's just going to go from 1. So this guy right here is hugely important in signal processing. You're trying to like send some information through any sort of radio or frequency. you can pick out what's the important part by encoding it here. And the person who's listening, the stuff encoded in these other ways doesn't really matter. If I wanted to, a little bit, and embed everything, then I could do that by modifying this function just a little bit. So modifying the frequency or modifying the amplitude, modifying will result in the modification of this peak. And for people in signal processing or any other like related fields, anywhere you're going to run Fourier transforms, this will be important. That's going to be a little bit over the heads of most people right now, and that's okay. But basically, yeah, anywhere you deal with signal processing or processing information coming in the form of frequency. Also, if you go into number theory, if you happen to choose to go into number theory, these are important there too. I'm sure other places as well. Those are just the ones I know off the top of my head. So let's come back to this. Looking at what we just did, does anybody have an idea how we could get started on this one?
Split the top from sine to cosine.
Good. I want to make one of the known limits show numerator.
Yep, sounds good.
Like this is doing that. Okay, I did go ahead and mute everybody. If you want to talk, just hold your space bar to talk, like a walkie-talkie. So I begin by rewriting tangent as sine x over cos x. And I'm doing that because I'm trying to get that sine x over x limit to show up. That's my goal. That's really the only thing I have that'll let me gain any control over something like this. The next step here is an algebra step, right? Understanding this fraction over a fraction thing. That's what's going on there. Dividing sine x over cos x by x is the same as multiplying it by 1 over x, which is the same as having sine x over x cos x. And I'm hoping that at this point we're all getting pretty comfy with algebra steps like this. It's something that we've done a lot, especially in those difference quotient limits. So this is just algebra. And then my next step is going to be to regroup. So I've got a sine x upstairs and an x downstairs. That's looking like the thing I want. But I also have that cos x downstairs. So let me just group them separately. This is sine x over x times 1 over cos x, like this. And now each of those pieces I know how to handle. The sine x over x piece, while not continuous at 0, it has a hole there. I do know that limit. That's my special geometric limit. And the 1 over cos x limit, he is continuous at 0. So in other words, I can treat this as this times, I'm just using my limit laws here, right? I can take the limit of each piece separately. So the limit of this product is the same as the product of the limits. The sine x over x limit I know is 1. And then 1 over cos of 0, got no problems with that. I can just plug in x equals 0 here. The cos of 0 is 1, so this is 1 times 1 over 1, which is 1. So the tangent x over x limit looks a lot like the sine x over x limit. These both say something really cool. So before I leave these examples, first questions on the mechanics here, what we did.
Yes, I have a question.
Yeah, go ahead.
Okay, so we went from sine to cosine over x, and then you went from sine x over x cosine. Shouldn't there be a cosine right next to the sine x?
No. So sine x here, I'll come in here and do the algebra gently. So if I've got sine x over cos x, all divided by x. That's the same as sine x over cos x times 1 over x, right? So dividing by x is the same as multiplying by 1 over x. That's the kind of idea there. Or in other words, I'm thinking of the bottom as being x over 1 as its own fraction. So I leave the top alone and I flip and multiply by the bottom. And that's the same as sine x over cos x times x, like this, which is what we have here, just with the multiplication downstairs written differently.
Thank you.
Yeah, no problem.
And then you just separated them? So
Yep.
you put sine with x and then 1 over cosine?
Yes, sir. Yep. In the same way that like 2 over 3 times 5 is the same as 2 over 3 times 1 over 5, I can split this fraction up into the product of these two fractions. Imagine you were to multiply these fractions. We multiply straight across. So my numerator would be sine x times 1, and my denominator would be x times cos x. That's exactly what we had here.
Got it. Thank you.
Not a problem. Other questions on the steps that we use to find this limit?
For the test, we can draw out all of the stuff that we know on a piece of paper and just kind of spit it out and revert back to it throughout the test.
So if you wanted to do like a memory dump at the start of test, where you, at the start of the test, pour all the things onto a page that you're worried about forgetting or you want to be able to refer back to, I'm fine with that. But you can't do that before the test starts. So think of it the same way as an in-class test would work. And I know some of you have taken classes with me and are familiar with this, but not everybody has. So I don't allow you to bring in a formula sheet or anything like that, but I do strongly encourage that at the start of the test, for example, in trigonometry, you draw your unit circle so you don't have to panic about it later. That same sort of ethos will apply here. So treat these tests as you would any in-class test. At the start of the test, if you want to dump everything that you're worried about forgetting or stuff like that onto a page, that's fine. But we can't prepare formula sheets ahead of time. Is that all? Is that understood? Is that okay?
Perfect. Thank you so much.
Yeah, no problem. Okay, so I do have, before we talk a little bit about the chain rule, one neat application. And if I have anybody here going into physics or any kind of like engineering, this will be hugely important. So both of these guys, both of these guys have some serious meaning in physics. Especially if you've ever calculated the motion of a pendulum. Not super easy, not super hard, but you need to make a simplifying assumption about halfway through the process that comes from one of these limits. And they really both say the same sort of thing. We've seen that you can get the tan x over x limit from the sine x over x limit. But how do we really understand these? What are these really saying? When I say the limit as x approaches 0 of this apparatus is 1, so thinking about, let's just take one of these. This means, think about the language we used to talk about limits at the very, very start of the course. We said, oh, well, as x gets closer and closer and closer to 0, sine x over x gets closer and closer and closer to 1. Even though I can't plug in x equals 0 and get 1 out, I can talk about what happens as x gets closer and closer to 0. And that's this big idea in calculus, getting like as close as you want without really going there, getting very, very close. So what this says is if x is very, very close to 0, then sine x over x is very, very close to 1. That's really what this says. And there's another way of interpreting that. That is, if I'm just going to write this using these shaky equal signs for almost equal to. If x is almost equal to 0, then sine x over x is almost equal to 1. And if you multiply both sides of this relation by x, then you find this is the same as saying if x is very, very close to 0, then sine x is very, very close to x. Now, one of the things we are able to do at this point is calculate the tangent line to the sine function at 0. But I want you to guess at what that tangent line slope is going to be from this relationship. Here we say if x is super duper close to 0, then the function sine x, that wave, looks an awful lot like the function y equals x, that line. Check this out. I'm going to need to readjust my scales, aren't I? Here, we'll just use a fresh graph. We can do it here. Look very, very, very close to 0. The red is sine x, the blue is just x. And if we're looking super duper close to 0, it's hard to tell them apart. So if x is close to 0, then the red and the blue are hard to tell apart. If x is very close to 0, then sine x is very, very close to x itself. This is called the small angle approximation for the sine function. And physicists use this all the time. Mathematicians get really annoyed at physicists because when they see sine theta, they just replace it by theta all the damn time under the assumption that theta is small. It's actually a pretty good approximation. If you wanted to know what is the sine of 0.1, oh, look how close this is. And you say, okay, well, 0.1, if I look along the graph of the sine function, along the graph of the red function, when x is 0.1, y looks like it's about 0.1008, which would be very hard to calculate, right? Certainly by hand, it would be extremely hard to calculate the sine of 0.1. And nowadays we have calculators, but how do they do it? They're doing this. They're saying, oh, well, if I look along the sine function or along the graph y equals x, there's really very little difference between the sine's output and y equals x's output. So I might as well just use the blue instead of the red. So this is one of the most important applications of the limit stuff we've done so far. We won't see any use of that application here outside of calculating more and more limits. But in your physics class, certainly when you take physics 1 and you discuss the motion of a pendulum, which you absolutely will, this will be used. This will be used several times there. It'll also be used in physics 2 when you talk about certain electromagnetic phenomena. So this is called the small angle approximation for sine. Small hyphen angle approximation. For the sine function. Okay. So one other thing we haven't done yet that we really should do is calculate some tangent stuff for these trig functions. Because now that we can, we have the trig derivatives, and then we should talk about the chain rule I don't want to drown you with chain rule stuff today because it's not on exam 1, but I do want to get the little intro out of the way. But first, let's do 1 or 2 examples using those trig derivatives. So let's find the equation of the tangent line to f of x equals sine x and g of x equals cos x when x equals 0. So we're going to calculate 2 tangent lines. I'm going to find the tangent to f at 0 and the tangent to g at 0. Just practice using our trig derivatives. F prime, so we need 2 things, right? I'll give myself space for both. So up here, I'm going to do the work for the first tangent line, and down here, I'll do the work for the second. Both of these, we need a point and a slope. For the tangent to f of x, my point is going to be 0, comma f of 0. And the sine of 0 is 0, right? F of 0 is 0. So my point for the first guy is just 0, 0. The point for my second guy, he's going to be 0, comma g of 0. What is g of 0? What is the cosine of 0? Anybody help?
1, 1.
Yeah, so the point of tangency for the second function is going to be 0, comma 1. All right, let's find our slopes. The slope here is going to come from f primed of x. The derivative of sine is cosine. So the slope we need is f primed of 0 is the cos of 0, which we just said is 1. So we can go ahead and write down the tangent line here. It's y minus 0 equals 1 times x minus 0, right? Using that point slope form of a line. Here's x1 comma y1. Here's m. But this is just the same as y equals x. And we saw that. Right? When we looked at that Desmos graph, we saw that the tangent to sine at the origin is the line y equals x. No big surprises there. So that's our first tangent. That is the tangent to sine x at x equals 0. Down here, my slope is going to come from g prime. The derivative of cos x is negative sine x. So the slope we need is g primed of 0 is negative sine of 0. But what is the sine of 0?
0.
Good. So what can you tell me about the tangent to cos x at x equals 0? What kind of line is it, the second tangent line?
Horizontal?
Very good. It's a horizontal tangent line. Yeah, perfect. All right, so I'm going to take my point slope form with this point and this slope now. y minus y1, that's y minus 1, equals m, that's 0, times x minus x1, that's x minus 0. This is the same as just saying y minus 1 equals 0, or y equals 1. So this is the tangent line to cos x at x equals 0, and this is the tangent line to sine x at x equals 0. And notice that the slope calculations no longer take up a whole page. Isn't that nice? No more huge limits to find these slopes. We can use our differentiation rules, and even here where we're talking about these trig functions, we can now use differentiation rules and get things done pretty quickly. I think maybe one more derivative calculation, something slightly more complicated to kind of remind you the other stuff we've been doing, and then we will move on to the chain rule. Really quick, in Desmos, I'd like to illustrate these tangents for you. So here's the one, right? Red is sine, blue is the tangent. I think maybe for the purposes of this, since we're going to look at two of them at once, I'm going to put the tangent dotted and in the same color as the original. So that is the sine function, and the tangent to the sine function when x is equal to 0. And we'll put cosine in green, and his tangent dotted green. All right, so here are the two functions, cosine and his tangent at 0, and sine and his tangent at 0. They look like this. All right, and you can see along the graph of the cosine function, this tangent being horizontal isn't really a surprise. The cosine has a little maximum there. That's a turning point for the cosine function. And we've seen horizontal tangent lines correspond to turning points in the past. If you haven't, play around with the other Desmos examples I have, like this one. And there's a link to it in the modules, but there's one other like this that I posted for you. One or two others like this. So you've got turning points. This isn't the good one, but yeah, turning points on the original corresponding to x-intercepts on the derivative. So play around with these graphs. Get comfy with these graphs. So Angelica asks, can we use dy dx to find the slope? Yeah, dy dx is just another notation for the derivative. Since on this problem, I wrote the curves as f of x equals and g of x equals, the notation that makes more sense to use here is the prime notation. But if you wrote dy dx instead, I would know what you meant. Just make sure that the notation you're choosing corresponds nicely to the notation that the problem is given in. The niceness of the prime notation here is if you just write dy dx, I'm not going to know which function you're differentiating, because here we had two functions. But the f prime tells me the derivative of f. So it's I wouldn't use dy dx here, but you could, and I would be able to tell what you were talking about probably. Okay. So let's calculate one more derivative. And then we're going to talk about the chain rule. Maybe we'll do it like this. Let's find any horizontal tangent lines to the curve y equals secant x. So I bet lots of us don't quite remember the graph of the secant function. Here, since I wrote, instead of f of x equals, I wrote y equals, this would be a good place to use the dy dx notation. So remember, HTL, horizontal tangent lines, come from places where the derivative dy dx is equal to 0. So we're going to find dy dx and then set it equal to 0. Dy dx, the derivative of the secant function is secant x tangent x. So that's the thing that we're going to set equal to 0 to find out where the original has horizontal tangent lines. How do you solve the equation secant x times tangent x equals 0? So this is why we talk so much about solving trig equations in MAC 1147.
We use the inverse of,
I'm sorry, say that again?
we use the inverse of cosine, or do we use arc cos?
I don't think that will help us here. So secant is the reciprocal of cosine, but not the inverse. You could rewrite this in terms of sines and cosines if you wanted to. That couldn't hurt. Let's try that, and that might lead us towards something like that. Some trig equations, you can use the arc functions, the inverse functions, to help you solve, but not always. And let's just take a look. So this is 1 over cos x, that's secant, times sine x over cos x equals 0. If we're not sure what else to do with a trig equation, rewriting in terms of sine and cosine is never a bad idea. We're setting the derivative equal to 0 because we wanted to find horizontal tangent lines. Remember, a horizontal tangent line is a tangent line whose slope is 0. And the derivative is what gives us the slope of the tangent line. We've seen a few problems like this in the homework. To find horizontal tangent lines, you take the derivative and set it equal to 0. So this is the derivative, and now I'm setting it equal to 0 to find places where the slope of the tangent line is 0, because tangent lines with slope 0 are horizontal tangent lines. So to find horizontal tangents, set your derivative to 0. And in that case, that means we need to solve this trig equation, secant x times tangent x equals 0. I can rewrite that trig equation like this, which is the same as saying sine x over cos squared x equals 0. And then I ask, well, how do I make that fraction sine x over cos x equals 0? I'm going to turn off my local cam here and just keep you guys on the dot cam if you don't mind. So this equation, does it look at all familiar to anybody from trig pre-calc? Does anybody have any ideas how we could solve it? Anybody?
Cosine squared x minus 1 equal to sine x or something like that?
Let's imagine that these weren't trig functions. Let's try to think in terms of algebra. If I had a fraction like this, I've had something like x over x plus 10 equals 0. You would just set the top to 0, right? Or you would multiply both sides by that denominator so that it goes away. In the setting of trig equations, we don't usually like to clear denominators because we could lose information. But this fraction will be 0 if and only if the top is 0. That's the big deal, certainly if the top is 0. So you can think of it like I'm multiplying both sides by cosine squared, and that just gives me sine x equals 0. For the purposes of equation solving, that's fine. Or you could think of it like this fraction will be 0 whenever its numerator is 0. That's the idea. So as long as the denominator is not also 0, a fraction is 0 as long as its top is 0. That's what we need, right? 0 over 5 is 0, 0 over 10 is 0, 0 over 1 is 0. So as long as the top is 0, this fraction sine over cos squared will be 0. So I set the top to 0. And then what are the solutions here? Does anybody remember how to find all the solutions to a trig equation like this? There was mention of inverse trig functions at the very start. You could get one solution to this equation by taking the inverse sine of both sides, but it won't give you all the solutions. So you may want to go back into your trigonometry notes and try to remind yourselves how to do this. It's a unit circle thing. If I want to find out everywhere the sine function is equal to 0, I need to look on my unit circle for all of the places where the y coordinate is equal to 0. So I want to address a few things I see in chat there. 2k pi will be a part of the solution for sure. There's actually a little bit more than that. And Carlito says if you do the inverse sine, it gives a syntax error. That should not be true. So real quick, off to the side here. One way to find a solution, but not all, is to take arc sine or sine inverse of both sides. If you go from sine x equals 0 to x equals the inverse sine of 0, which is what happens if you take arc sine on both sides, you go from here to here. The inverse sine of 0 is just 0. You should not be getting any syntax error there. If you did get a syntax error there, then something wasn't quite typed correctly. That will give me one solution to this equation. But I want all of them. And the way we think about it is along the unit circle, the sine function is 0 whenever the y coordinate on the unit circle is 0. So that's at this point over here and at this point over here. So what are the two angles here? This guy I can think of as being the angle 0. Right, I've rotated 0 radians from my starting point along the positive x-axis here. And this guy I can think of as coming from the angle pi. Now, since the sine function is periodic with period 2 pi, I end up with two infinite families of solutions to sine x equals 0. The first is x equals 0, this fundamental solution, plus 2k pi. Because the period of the sine function is 2 pi, I need to be able to add any multiple of that period back to it. Or another way to think of it is if you start here and you walk around 2 pi, you land back here. The other one is x equals pi plus 2k pi. So these are my two infinite families of solutions to the equation sine x equals 0. Depending on who you took trigonometry with, you may know that because these 2 points are evenly spaced along the unit circle, you can actually condense these into a single solution expression. Which can be written more compactly as x equals k pi. So this is 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. This is the nice way to say it. But there's nothing wrong with these. If you gave me these, I would say, okay, you're right. No arguments, 100%. But it's also nice to recognize that you can condense it like that. This approach, not so great. So the inverse trig stuff is useful in a lot of ways. Yes, Nicholas, there will be. I appreciate you saying that. We'll come back to that in just a second. The problem with using the inverse trig functions to solve your trig equations is that trig functions are periodic. So most trig equations have infinitely many solutions. We don't want just one solution. We want all of the infinitely many solutions. So this can be an okay way to get started if you're lost on figuring out where to go. It can be an okay way to get one solution if you only care about one solution. Like if I said just find the solutions to this equation from -π/2 to π/2 or something, that would be okay. But when you're trying to solve a problem like this in general, we need to be comfy with this unit circle approach and this thing of adding multiples of the period. And then ideally we'd also be comfy with this condensing into a smaller set. But I'm not going to beat you up over this. As long as you can get here, we're okay. So Nick asked a really good question in chat. What about that denominator? We didn't just have the equation sine x equals 0. We had sine x over cos squared x equals 0. Are there any restrictions that come from that? Yes. But they're not going to affect us here. So we would need to make sure that whatever our solutions are, here x equals k pi, so any integer multiple of pi, we need to make sure that this guy isn't undefined at any of those. It's possible that some number makes the top 0 and also makes the bottom 0, and that would be bad. In those cases, we would need to investigate with a limit or just throw them out because they make the bottom 0, the thing is undefined. That would really be the way to handle it here. Just like you did in your trig classes. So when you solve these equations, if your last step involves setting the top to 0 or multiplying by a denominator and canceling it, then you need to make sure that that denominator isn't 0 at any of your solutions. Is that a problem here? Where is cos squared of x equal to 0?
Are we saying that we're bouncing back and forth from the unit circle twice?
I don't quite follow the question. So what was the question?
I'm sorry, I don't know.
No, it's okay. It's okay. There's nothing wrong with asking. I'm just curious what it is. Whatever you're thinking there, I'm sure other people are thinking it too. I'm just not sure what it is.
The cosine square of x, right?
Mm-hmm.
So I'm looking at where my value of cosine is 0, right? But it's square. Wouldn't that mean that it's just a thought I'm throwing out there. Does it mean that I'm bouncing on the unit circle one way and then the other way?
I got what you're saying. So it's not actually that complicated. That's a good thought, but it's not that complicated. To find out where cosine squared is 0, you just need to know where cosine is 0. Right? Cosine squared, remember, is cosine times cosine, and that product will only be 0 if cosine is itself 0. So even though there's a square here, so we need to stay away from any x values which make the bottom equal to 0, which is the same as saying cos squared x equals 0. But the good news for Aubrey's question here is that cos squared x is going to be 0 if and only if cos x itself is 0. So we don't need to do any funky geometry there from the square. You can think of it like taking square roots on both sides to go from here to here. The square root of cos squared is cos, the square root of 0 is 0. So those would be coming from the north and south pole of the unit circle. So cos x would be 0 when x is pi over 2, 3 pi over 2. And then you can periodically extend if you want to. This would be like 5 pi over 2, 7 pi over 2, and so on. Odd multiples of pi over 2 are what make the cosine function 0. And there's no overlap between this list and this list. And the easiest way to see that is because they're coming from different points on the unit circle. So we're safe.
So with that being said, you can just ignore the bottom.
On this problem, yes.
Got it.
On this problem, the denominator doesn't introduce any extra restrictions, and it could never give us extra solutions. So the solutions, when you set some mess of shit equal to 0, always come from setting the top equal to 0. And then you may also get some restrictions from the bottom. Think about what you learned about rational functions in pre-calculus, right? They say find the x-intercepts, you set the top equal to 0. Oops, but make sure that there isn't a factor in the bottom that could cancel with that top, right? Because maybe that's a hole instead of an x-intercept. Same sort of shit.
Right.
So if the top and bottom were 0 at the same time, we might not have a solution to this equation. We would have like a hole in this graph rather than an x-intercept.
Cool, thank you.
Of course, yeah. So luckily here, there's no overlap between these two solution sets. And we can see that because they're coming from different points on the unit circle, or we can see that by writing them out. We could have gotten one of the solutions from the inverse trig stuff, but really we don't want to do that. We want to make sure that we're comfy with this unit circle argument right here. This is the money. And then the question is, all right, well, great, what the hell do I do with this? What is it we were trying to do? What is this supposed to have found? Anybody remember what our original goal was?
A horizontal tangent line.
Yeah, we wanted to find the location of on the secant function. So here's in all of its wonky glory. Does anybody see any locations of horizontal tangents? About there.
1 and -1.
Yeah, well, so up here at 0, comma 1, down here at pi, comma -1, over here at -pi, comma -1. What would be, according to our work here, according to this solution set, what would be the x value at another horizontal tangent? So far I've got this guy at 0, comma 1, so x is 0, this guy when x is pi, this guy when x is -pi. Who can give me another x value where I expect from this, the secant function has a horizontal tangent? What do we think this guy over here is?
2 pi.
Yeah, right? Because all of these horizontal tangents are occurring at k pi, integer multiples of pi. So this guy is going to be x equals 2 pi. What's the y value there? What is the secant of 2 pi?
1.
1, yeah. There it is. So all of these are locations of horizontal tangents. And in general, they occur at any integer multiple of pi. And that's what we said over here. We should get horizontal tangents when x is any integer multiple of pi. So that's it. Does that make sense? We spent a lot of time talking about things here, but the actual solution process is fairly quick. Take the derivative, set it to 0, solve the equation. With trig functions, that means solving trig equations. So especially if your trigonometry class didn't spend a lot of time on that, you're really going to want to go back and grind on that for a bit. Solving trig equations, hugely important in Calc 1. We do a lot of this. Questions on this example? Kind of move things so we can see it all here. Remember, the solution itself is just this stuff. All of this is kind of extra discussion. These guys were not a part of the solution set. These were places that made my denominators 0. These guys were a part of my solution set, so I needed any angle that landed me at either of those points on the unit circle. And those are 0 plus 2k pi and pi plus 2k pi, which could be condensed into just k pi. All right, let's see how we're doing for time. We are getting close. Are there any questions here that we want to tackle? Okay. I have a question or two for you. Can we find, and this is the start of our discussion on the chain rule. I'll just call it Y. What else should we be able to do like this? I guess this is a good enough start. Could we find the derivatives of these guys? Or what about or this guy? There certainly will be a fair amount of trig on this exam, yes. I don't know what too much would be. It's hard to say. It's not an easy question to answer. The question that came in chat, will the exam focus too much on trig functions? The question distribution will be similar to the question distribution in the study guide. Let's say it like that. Okay, so my question to you here is, can we find the derivatives of these functions? These functions all have something in common. They're all composite functions, meaning they're all functions within functions. Here I've got my exponential function e to the x, but then I've plugged 2x into that. Here I've got the sine function, but I've plugged 2x into that. I could have plugged pi x or even e to the x into the sine function. These are all composite functions, i.e. y equals f of g of x for some choices. Of f and g. So the trick to differentiating composite functions is the chain rule. As some of these we can get around. But some of them we need the chain rule. So what I'm going to do is I'm going to give you the chain rule here. I'm going to show it to you. Just to be clear, this is not on the exam, right? So this is the start of new material. This is section 3.4, which is not on exam 1. So this is the last little bit of new stuff I'm going to give you. Wednesday we will be studying on the exam. Friday will be the exam itself. But I just want to prime you for what we will be doing after the test, because it's a little bit tough. People tend to have a hard time with this. So I want it sitting in your head a little bit before we actually make you do it. What the chain rule says is if you want to differentiate a composite function, then the derivative y prime, or you could write this as dy if you wanted. You differentiate the outside function, leaving the inside alone. Then you multiply by the derivative of the inside. This is definitely the most important of all of our differentiation rules. Product rule, quotient rule can all be taken as a consequence of this. So it's important that we take our time. Like I said, that's why I'm showing it to you now, so it can bake in your brain for a little bit before I actually make you use it. You will not need the chain rule on exam 1. You don't need this for test 1. So if you're the sort of person who just wants to focus on exam 1 material, you don't want to think about anything that's coming up at all, you can tune out a little bit. Don't panic. We're going to go back over this next week after the test. But I just want to show you so you can start getting a feel. And if you're the sort of person who likes to think ahead a little bit, I encourage you to take careful notes here. So this theorem is called the chain rule. And it says to differentiate a composite function, differentiate the outer function, leave the inner guy alone, then multiply that whole mess by the derivative of the inner function. So for example, if I look at y equals e to the 2x, my outer function here is the exponential function, and my inner function here is 2x. So here, this is f of g of x, where f of x is e to the x, and g of x is just 2x. You see, if I plug g into f, I do get this. So by the chain rule, y prime, derivative of this, I'll differentiate the outer thing, and remember the derivative of e to the x is e to the x, so I leave the e to the 2x alone, and then I multiply by the derivative of the inside. The inside function is just 2x, so that looks like this, and then I can clean that up. That's e to the 2x times the derivative of 2x is just 2. This is 2 e to the 2x. If I wanted to differentiate the sine of pi x, this is a composite function where f of x, the outer function, is sine x, and g of x, the inner function, is pi x. And you see, if I plug g into f, I do get this. Which means, by the chain rule, y prime would be the derivative of the outside, differentiate the sine function, leaving the inside alone. So if I differentiate the sine function and I leave the inside alone, the derivative of sine is cosine. I leave the inside alone. But then I need to multiply by the derivative of the inside. So here I've differentiated the outer function, the sine function, leaving the inside alone. And then I multiply by the derivative of the inside. The derivative of pi x is just pi. This is cos pi x times pi, or pi cos pi x. This is how we use the chain. I'm going to show you lots of other examples, but that's going to wait until after the exam. So after exam 1, I will show you a whole shitload of examples using the chain rule, and then you'll be able to differentiate things that look horrible and terrifying and scary, really, really big things, using combinations of the product, quotient, power, and chain rules. The chain rule is the hardest one to use, but it's also the most important. It's going to take a little bit of practice, maybe easier to use perhaps than the quotient rule. I fuck up the product rule or the quotient rule from time to time, but I never fuck up the chain rule. Because once you get comfy with it, it makes good sense and there's very little memorization, whereas the quotient rule, a lot of memorization. But if this is something that you just don't want in your brain right now because it's not a part of exam 1, that's understandable. But maybe come back and rewatch this video after exam 1 or the last few minutes of this video to kind of set you up getting ready to talk about what we're going to do after the test. All right, so hang it up for today.
Good question.
Please bring questions to the guide. And I want to remind you that the purpose of the study guide is so that you can bring questions to me in office hours or via email. The main idea is to give you some problems that are exam level difficulty that you can discuss with me so I can get to see your work a little bit before the test and you can get to hear my thoughts on your work a little bit before the test. So please, everybody, at some point this week, send me an email with a picture of your work or like come by an office hour, do something so that you and I have had a little bit of a back and forth regarding your work specifically, like how you write things on the page. The easiest way to do it is to come by office hours and show me something and be like, hey, does this look good? And I'll either just say, yeah, it looks great, or make sure you write this that way. Doing that before the test saves you a bunch of headaches. Also, if you haven't yet, please read the instructions that I posted to Canvas saying how to take the test and how to turn in the study guide. If you don't read those instructions, there will be issues because things are not quite as simple as you might imagine them to be. It's very important that you scan and upload your work and that you do it according to a certain schedule. You need to, especially for the exam, scan and upload your written work quickly after you finish the test in WebAssign. Finally, if you haven't done yet, please take the practice quiz in HonorLock. So if you go to our Canvas page, there's an HonorLock link on the left. The instructions for this are in the Canvas post I just mentioned, the announcement. But make sure that your computer can run through the HonorLock process. Like make sure your webcam is good enough to get a clear picture of your ID. Make sure that your microphone and settings are sufficient for doing the room scan and all the monitoring things they want. Make sure you have the browser extension installed in Chrome, all that good shit. That way on Friday, on the day of the test, there won't be any problems. Okay?
Oh, Professor, I have a question.
Sure.
What do we do if our internet basically goes off? Because yesterday I was taking a test for another class, and when I was like about to finish the test, it basically went off and I couldn't do anything. I had to contact the professor, and he doesn't use HonorLock, so it was a lot easier. And I've never used HonorLock, so I don't know what will we do if that happens, because I'm sure some people in this class haven't used that.
That has happened to students of mine in the past, and when it goes out, the internet comes back, you sign back into HonorLock, you'd have to run back through that verification process. So it is a little time consuming. So if that happens to you during your test, you should contact me. I will add some time to your test to make up for the time lost having to log back in. And then you just go back through the HonorLock process and start. You shouldn't lose your information as long as you submit your answers in WebAssign as you go. So in WebAssign, each question has that submit button. Make sure that you're submitting answers as you go so that they're saved, so that if you got kicked out, not all is lost. But since you'll be writing down your solutions on paper as you go, even if that happens, you can just type them back in. So yeah, if you get kicked out, just let me know and then start working to come back in. Let me know so I can add some time, and then you'll be able to finish up your test.
Okay.
I know that the online testing stuff is a hassle. I hate it. I don't blame you if you hate it. But we're going to make it work as well as we can. And that's kind of all we've got right now, unfortunately. I know it's not a really great answer. Our stuff, we've got to kind of try. But I promise I'll be as accommodating as I can. Any other questions before we sign out for the day?
Yes, in regards to your last example with the chain rule, where do you get the cos from? Is that because that's a derivative of sine? Yeah,
so the cosine function here.
Yeah.
So I differentiated the outer function, which was the sine function, and I left the inside alone. So the derivative of sine is cosine, and I leave the pi x on the inside alone. And then I multiply by the derivative of the inside function.
Cool. Thank you.
So I think of this as kind of like peeling an onion, right? Like you differentiate the outer layer, that leaves the inner layer, but it doesn't do anything to it. Then you peel the inner layer. So here's differentiating the outer layer, and then we multiply by the derivative of the inner layer. And you can actually keep going. You can stack it like that. But yeah, that's where the cosine came. Derivative. Any other questions here, guys?
Nope, we'll see you at 1 o'clock.
Okay, that sounds good. I'll see you guys either in office hours or in class on Wednesday. Remember to bring questions for the review on Wednesday, all right? Wednesday, I would like to discuss study guide problems. Bring the ones that you want to talk about so you know which ones to work. Most by and share some of the written work. That is it.